Welcome to The Explainer. Today, we're diving into the really strange and super colorful world of coordination compounds. Now, these are chemical structures that are, well, they're absolutely everywhere, from the hemoglobin in your blood to the chlorophyll in plants, and they follow some very, very unique rules. To see what I mean, let's just start with a little chemical puzzle.
Okay, so check this out. On the left, you've got something called a double salt, and on the right, a coordination compound. They look pretty similar, right? But watch what happens when you put them in water. The double salt just disintegrates. It breaks apart into simple little ions, completely losing what it was. But the coordination compound? Nope. It holds together, staying as one single stable unit.
So what gives? What's the secret here? What kind of special chemical glue is holding that coordination compound together when it's dissolved, while its cousin, the double salt, just completely falls apart? Well, that is the exact mystery we're going to solve today. To get to the bottom of this, we're going to treat it like a proper investigation. We're going to peel back the layers one by one to see exactly what's going on. And that means we have to look inside the complex itself. Let's, deconstruct this thing and meet the key players, starting with the most important one. So the star of the show is something called a ligand. A ligand is basically any molecule or ion that latches directly onto that central metal atom. Now, the crucial thing to understand here is that ligands are electron donors. They give a pair of their electrons to the metal, and this forms a special, really strong connection. And that is the secret to how they hold together so well. But not all ligands connect in the same way. The simplest ones are called unidentate, which means they grab on at just one point. Think of it like a single handhold. Then you have bidentate ligands, which grab on at 2 points. And, you guessed it, polydentate ligands can have many connection points. It's really the difference between grabbing on with one hand, two hands, or a whole bunch of hands at once. And this is where it gets really, really interesting. When a ligand grabs that metal atom at 2 or more points, it often forms this kind of closed ring. This is called a chelating ligand. And that ring structure it creates, it makes the entire complex incredibly stable. I mean, it's just much, much harder to break a two-handed grip than a one-handed one, right? And the name itself gives us the absolute perfect mental image. Chelate actually comes from the Greek word for claw. So you can literally picture the ligand clamping down on that metal atom, locking it in a grip that's just incredibly difficult to break. This whole tightly bound unit, the metal and all its claws, is called the coordination sphere. And we show it by putting it all inside square brackets. So this solves our initial mystery. Everything inside those brackets acts as one single unit, and it will not break apart in water. Only the ions that are outside the brackets can float away. So we have the sphere, the ligands, the claw. But how in the world did anyone figure all this out? Well, that brings us to the very first person who drew up a blueprint for these amazing structures. Let's go all the way back to 1893. A chemist named Alfred Werner came along and proposed a truly revolutionary theory. You have to remember, this was at a time when chemical bonding was still a huge mystery. So his ideas about coordination were just a massive, massive leap forward. At the heart of Werner's theory is this idea that metals have two different types of bonding capacity. The first is the primary valency. Think of this as just the metal's charge. It's balanced by simple ions that can break away in water. But the secondary valency, that's the crucial one. That's the number of ligands locked inside the sphere. This bond is directional, it's non-breakable in water, and it's what determines the complex's final 3D shape. Werner's blueprint was brilliant for figuring out the structure, but it couldn't explain everything. In fact, one of the most striking features of these compounds was still a complete mystery. Why are these things so brightly colored? I mean, really vibrantly colored. And why are some super stable while others are really reactive? To answer those questions, we needed a more powerful model, one that could explain not just the structure, but the properties we can actually see. And that model is called crystal field theory. Okay, crystal field theory starts with a free metal ion, all by itself. Its 5d orbitals, which are just the regions where its electrons hang out, they all have the exact same energy. The technical term for this is degenerate, But just think of them as being perfectly level and balanced. Now, watch what happens when the ligands start to approach. Remember, ligands are donating electrons, and those electrons create this kind of electric field that repels the electrons already in the metal's d orbitals. It's kind of like bringing the negative ends of two magnets close to each other. They just naturally push back.
And because those d orbitals have different shapes and point in different directions, this repulsion affects them differently. And the result? The once equal orbitals get forced apart or split into two groups with different energy levels. This energy gap that's created, that's the real key.
And that energy gap is the secret to their color. An electron can absorb light of a very specific energy, which corresponds to a specific color, to make the jump across that gap. The color we end up seeing is simply all the light that's left over. This theory perfectly explains not just their amazing colors, but even their magnetic properties.
Okay, so we've solved the structure and we've solved the color, but there is one final, really fascinating twist to this whole story. What happens when you use the exact same chemical parts, but you just arrange them in different shapes? This brings us to the idea of isomers. These are compounds that have the exact same formula, the same list of parts, but a totally different layout of the atoms. And that different arrangement, as you're about to see, can change literally everything about the molecule.
So a common type is what we call geometrical isomerism. Let's imagine a complex where two identical ligands are right next to each other, at about a 90-degree angle. This is called the cis isomer. Cis just means on the same side.
But what happens if those same two ligands are across from each other, on opposite sides? Well, that's the trans isomer. Now, it's the exact same set of atoms, but the cis and trans versions are completely different molecules. For instance, the powerful anti-cancer drug cisplatin, that's the cis isomer. Its trans counterpart, it's biologically useless. Arrangement really is everything. And that just leaves us with a final thought to chew on. We started with a simple observation about dissolving salts, and it led us down this rabbit hole of claws and spheres and energy gaps. It just proves that in chemistry, the parts you have are only half the story. The other half is how you put them together. So if the same atoms can build entirely different molecules just by shifting their position, what other incredible chemical secrets are still hiding right out in the open, just waiting for us to see them from a new angle?